So, questions about what we ended yesterday with in terms of the if I give you a reaction, how can you determine a couple reactions, which one goes faster, which one slower, whether they have the same rate? Let's start with a few of them, just kind of to go back and remember what we did. So here's two reactions. The question is, which one of these two reactions goes faster, A or B, or if they have the same rate, then you would choose C. Okay. So there's three to start with. Which reaction goes faster, the A reaction, the B reaction, or the C reaction? Actually, I may. And there's the fourth one. So we're going to do them one at a time. The negative charge is on the C, so it's a Cn minus. The Cn minus would be a C triple bond and with the minus charge. But the critical part of that is the negative charge. What's different about number 4 as the solvent? So, let's go through these one by one and see what we got. Okay, so we'll start with number 1. With A, which one is faster? A, B, and if they have the same rate, they're going to be C. Okay. All right, for number 1, we have 7 A's and 4 B's. And no C's. So question number 1 is, what is the mechanism of those two reactions? SN1. Do we all agree with that? Why? The critical part of this is we got a secondary and a tertiary plus a weak nucleophile. The weak nucleophile can only undergo SN1. So that's, and the secondary can form a secondary carbocation, so that mechanism then is going to be SN1. What's different? Secondary versus tertiary halide in an SN1 reaction, which goes faster? A secondary versus a tertiary. A tertiary. So which one would go faster? B. Out of curiosity, if you answered A, what was your reasoning for A? Okay. So sterics will only matter if it's an SN2 reaction. So that's why our first step is always to determine the mechanism. And then what's different, and then how does that difference, how is that affected in the mechanism? So this is an SN1 reaction because it's a weak nucleophile. What's different is that we've got a secondary halide versus a tertiary halide. And so we have to ask ourselves, in an SN1 reaction, which reacts faster, a tertiary halide or a secondary halide? And so the question really is, which one forms the more stable carbocation? Because the halide that forms the more stable carbocation will react faster in that first rate determining step. And so in this case, tertiary reacts faster. And so this tertiary is going to form the carbocation faster, so that means that B is going to be reacting faster than A. Okay. So how about number 2 then? Which one reacts faster in number 2? A, B, or they have the same rate, C? I think, Hannah, I got all but yours, because there we go. It doesn't tell me how you voted, it just put your name up so that I know it counted it. And I think this, Alex, can you? I think the sunshine is in the way. Okay. So, I said stop. All right, we have a 1 to 10. B reacting faster. So again, what kind of mechanism is this? SN2, because it's secondary plus a strong nucleophile. So it's SN2. What's different? The leaving group. Does the leaving group affect the rate of an SN2 reaction? Yes, because it's in the alkyl halide is part of the rate equation. Does the leaving group affect an SN1 reaction? Yes. And the leaving group will actually affect all 4 of the reactions that we talk about, because the alkyl halide is in the rate equation for all of them. So better leaving group then is, right, so which is the better leaving group here? The iodine is the better leaving group because it's the weaker base. It's farthest down on the periodic table, so therefore B is the correct answer. Yes?
I think I'm being tripped up on some of the secondary. I got the answer right, but I thought it was a primary carbon.
Okay. Yeah, so what are the definitions of primary, secondary, and tertiary? So the first thing that we have to do is we've got to look at the carbon that has the halogen, that's attached to the halogen. That's what I'm determining is primary, secondary, or tertiary. And what primary, secondary, and tertiary means is how many carbons are attached to that carbon. So it's the carbon that's attached to the leaving group, how many carbons are attached to that CH2? Just 1. So that makes that primary. If I had that one, again, focusing on the carbon that's attached to the halogen. And the halogen and oxygen, they don't count for primary or secondary. It's only the carbons that are attached. So how many carbons does that have attached to it? 2, and so that makes it secondary. And then the tertiary, like a tertiary butyl chloride, it's the carbon attached to the leaving group. How many carbons are attached to it? 3, so that makes this carbon tertiary. Why isn't question 2 primary? It is. I probably said secondary, right? It's a primary halide. Because it's CH2 and then the CH3. And if you have to still write these in, you're better off to do that. So it's primary plus strong nucleophile. It's SN2. Number 3. Oh no. Hold on. Okay, we've got a 3, a 2, and a 6. So, mechanism, SN1, tertiary halide. That's all the farther we need to go. Tertiary halide's got to be SN1. What's different? The nucleophile. Does the nucleophile strength affect the rate of an SN1 reaction? No? So for an SN1 reaction, the overall rate equation is only dependent on the alkyl halide concentration. Because the first step is to form the carbocation. That's rate determining step. So will the concentration or the strength of the nucleophile affect the rate of that reaction? No. So if that's the case, then they're the same. However, my question is for somebody who answered B, and why you answered B. Nobody answered B? Except the 2 people that answered B? Why'd you choose B? I'm not going to tear you apart. Because if you chose B, you could be correct. If you looked at it in a particular way, your reasoning is perfectly okay. Brandon, did you have B?
Yeah, the electrophile, the nucleophile group, the one that is neutral.
Okay, because they're both neutral nucleophiles.
Right. Because when we were talking about the probe and neutral.
Okay, so those nucleophiles are also solvents for the reaction. So if you chose water being faster, it's because water is more, because it's a hydroxylic solvent. Actually, they're both hydroxylic solvents. But which one's more polar? Water. So water being more polar would actually do a better job of solvating the ions once they're formed. So if you looked at water and methanol not as nucleophiles but also as solvents, the B would go faster because it's a more polar solvent. So if you looked at it that way, that would also be an acceptable answer. That this is a more polar solvent. Now, if you said, I didn't really know we're supposed to take polarity into account, they're both hydroxylic solvents, okay. Then you would still have them having the same rate. And of course, to say that the more polar solvent makes the reaction go faster, it has to be only for SN1, because for SN2, that slows the reaction. So I would accept B as well. How about number 4? Number 4, let's see. What do you have for number 4? That.
It's just the
But since we're never going to see the sun, we might as well keep it open on days where we do. 731. Alright, this is getting tedious, but mechanism. SN2. What's different? The solvent. So in terms of the solvent, you can think of it one of two ways. Which solvent speeds up the reaction, or which solvent slows down an SN2 reaction? A product speeds it up because product slows it down. Okay, and that points us towards which answer? A. So A is the correct answer. So SN2, different solvent, A product versus product. The product slows it down because it solvates the ions that are the nucleophile that's trying to react. Yes. So product and A product, basically product is something with an OH group, and A product is something without a OH group. So that's where yesterday I had product equals hydroxylic and A product is equal to non-hydroxylic. So when they talk about product and A product, they're really talking about OH groups. Yeah.
A lot of these questions had just the names of solvents. So is there a keywords or something?
So they had like what, DMF, DMSO. What did they put for methanol? Okay, so really the ones you have to remember that are product are alcohols like ethanol and water. Everything else is an aprotic solvent. Acetone, DMF. And those are the ones that I laid out yesterday in here. So acetone, DMSO, DMF. I don't know if they have acetonitrile or not, but basically the only ones that are going to be alcohols like ethanol and then water. And I can't see them using more than ethanol as the alcohol, because they're not going to say propanol or butanol but ethanol, water would be the two product solvents. So would you have to do this on the exam on Monday? Yes. Okay, so you have to think through the reasoning and the steps. First thing you need to know is the mechanism. And again, when I give you a problem, I will not give you a problem that has two different mechanisms, because we can't tell the difference between an SN1 and an SN2 rate. It's apples and oranges. So you'll have to do that. And that's one of these, those are the kinds of problems that combine basically multiple concepts together. So does that make sense to everybody, those? And there's more of those problems in Monday's folders practice problems and in Tuesday's practice problems. The ones we did yesterday in class were practice problem 2 from Tuesday's folder. So there's still problem set 3 and a problem set 1 that has some of those on them, as well as what's in Top Hat. And I'm sure if it's in Top Hat in the chapter, there's probably some at the end of the chapter problems, which again you can do as practice, that would be the same thing. Basically, unless I ask you for reasoning, this is kind of like a multiple choice question of which one goes faster. Okay, mechanisms. So if I said, let's write the mechanism for hydroxide plus write the mechanism and the products for, and identify the mechanism for this reaction. So I might combine all of that together. I might say, number 1, what's the mechanism? Number 2, write the mechanism step by step, and then give me the products. And I will also say, show the stereochemistry of the products where it's appropriate. Now, when is it appropriate? It's going to be appropriate when I show you the stereochemistry of the reactant. So anytime you see bold and dashed wedges used in the reactant, you're going to have to show me the bold and dashed wedges of the product. So can you write the mechanism with the arrows, with the transition states of this reaction? And then, if you can blow through that one, let me put bold and dashed wedges in here. Can you write the steps, arrows, charges, transition states, intermediates for these two reactions? First thing you got to do is, what is the mechanism, so that way you know what mechanism you're going to be doing. You got to show all the arrows. So for the first one, that's a secondary halide plus for primary. So they have to think, okay, what's an SN2 mechanism? How many steps? What's the transition state? First arrows are okay.
You have to put your media file at the chapter or back and forth.
It's always backside. So you have to show the arrows the nucleophile attacking and the reason for its leaving, transition state, with the charges, one. No, what's going to happen is that basically that molecule is starting out like this. It has nucleophile attached to the fat. And then after it's done, well actually no, sorry, it's starting this way. So the nucleophile is coming out of this. That's the flat out. And then so the OH is going to be the same. It's going to be the primary point of the cathode. It's the left, and everything else kind of works and flips it. But it's going to be on the same boulder dash wedge that it started out with. So it started out with this thing. It doesn't really matter where it goes. As long as they're on the same, because those three bond, the bond, the CH3, the H, F, they have to stay on the same bond. So the CH3 starts at the front. It still has to be in front of the other side. It just has to be in front of the other. So you're okay. And then the OH and the Cl are on dotted on the side because they're effective, but because they're effective. It's string one. Right, and they're all still on the same wedges. So the F will still on the bold wedge, it has to be on the bold wedge. It's just as important to the left, it's not important to the right. No, you were okay. That's okay. What you wrote was fine. And then when you double check, if you're, whatever the configuration was of the carbon in the reactant, it should be opposite of the carbon. It should be at step. So you got the first one. So you just want these bonds to be trigonal by pi.
Okay, so it'd be like up and down.
Yeah, so they're up and down.
But like,
That's okay.
they're doing both like,
Well, they're 180 degrees at partial bonds.
okay. So like the dots are like
The dots are-
over there.
It can go behind, it would go, technically it would go behind the F group,
Okay,
but you can show it slightly off on either the left or the right hand side.
okay, and then for the final,
Everything's gonna be, so these should be pointed at this. So yeah, so I think it's just really not really the type of
or like that, and
the OH can go there. Yeah. So now if you did number 1, number 2, number 3, versus up here, number 1, 2, and 3. So this is R, and that is S. So you're good.
and then the arrows.
So arrow comes in from the OH to the carbon,
Okay,
and then from the carbon-chlorine bond it gets kicked out.
so it can just be going like, okay,
Yeah. Well, it's actually going to the core. The bond is going to the core because you're breaking the bond and giving the pair of electrons to the core. So, yeah. So that's starting now is so then you don't put well, so that's and then, how many steps should there be for the second reaction, for the SN1 reaction? How many steps? 2, 4. No, there's 3. There should be 3 steps for the second reaction. Yeah. It's reaction of a alkyl halide with a tertiary with a neutral nucleophile, so you should have 3 steps. Which is something we have to remember
yeah.
when we're writing it. So it needs to have 3 steps, not 2.
I think charging.
Yeah, your charges are a delta minus on that.
Okay. So like, once it goes into the transition state, it loses,
It goes to a delta minus because some of that charge.
because it's only partial, okay.
Because some of that charge is being transferred.
And then this one's like,
Yeah, it's full.
okay.
Right, so then just cross out the U. So it looks like everybody was okay for the SN2. Eventually. So the critical parts here for the SN2, and we'll do the SN1. We'll go through step by step. So this OH minus is going to come in and attack the carbon, and then the pair of electrons goes to the chlorine. So that's number 1. That's the first thing that you have to have for that mechanism is this pair of electrons going to the carbon, and that pair of electrons going to the chlorine. The transition state then is going to have a dotted line to the carbon and a dotted line to the chlorine. So in the trigonal bipyramidal transition state, the OH and the Cl are linear. And then the other three positions, so you can either have one up and two down, or two up and one down, it doesn't matter. But all three of these groups, the methyl, the hydrogen, and the ethyl group, are pointed to the left here. They're going to flatten out. But what doesn't change is the bold or dashed line that they're on. So if you wanted to write this with a hydrogen or with the methyl group up, the methyl group has to be on the regular bond, the one that's in the plane. And then your hydrogen or your ethyl group would be on the bold wedge, and then your hydrogen would be on the dashed wedge. And so you could have your transition state with the methyl group up, or you could have a methyl and a hydrogen up and the ethyl group down. What's critical is that these three groups are relatively straight up and down. And that they are on the same bold or dashed line that they started out with. It is right now. It actually is right now. The H will be on whatever it started as. So in this case, the reason I put the H on the dashed wedge is because to determine the configuration of this, it's 1, then 2, then 3, because I already put the hydrogen as 4 on the dashed wedge. So now going from 1 to 2 to 3 is going to be clockwise. So that means that I started with R. Which means when I'm done, that chiral center has to be S. And what am I missing with this transition state then? A delta minus on the oxygen and a delta minus on the chlorine. Okay, so those are the critical things. Whatever that wedge or regular bond the groups are, they have to stay there because they're basically inverting and flipping over. And then for the final product, what happens? What happens is that if I just look at the carbon and the three groups other than the OH, they're now going to flip from the pointed to the left to pointing to the right. So that means the CH3 is going to be up, but on a regular line. The hydrogen's going to be on a dashed wedge, and the ethyl group is going to be on the bold wedge, but now instead of pointing to the left, they're all going to be pointing to the right. Because where does the OH go? The OH is replacing the chlorine in that second position that's in the plane of the paper. And so now if I looked at this, OH1, ethyl 2, methyl 3, the final configuration here is S. So if you do it this way, where the OH basically replaces the chlorine on the left in the plane position, then you'll get inversion of configuration. And I check that. That's the one thing I check. So if you did it some other way and your product's in some other orientation, as long as it's S, it's okay. If it's R, it's not completely correct. So typically for a mechanisms question, they're usually about 15 points, and I just make it fit whatever that 15 points is. If you look at this, there's 3 distinct parts here to an SN2 reaction. There's the first 2 arrows, there's the transition state, and then there's the final product. So it's critical to have those first 2 arrows there because that's 5 of the 15 points. Right? If I make it relevant to what everybody values, which is points. You want to make sure you show those 2 arrows. In the practice problems, problem set 1 is Mondays, problem set 2 and 3 are in Tuesday's folder. There are writing mechanisms problems, and there are narrated answer keys that go with it. So you're going to want to, well, it's up to you if you want to try some practice problems before Monday, because I am going to ask you to write an SN1 and an SN2 mechanism. So this is SN2. Always the arrows, transition state, final product. If I show you the stereochemistry, which I probably will, you're going to want to show the stereochemistry of the final product and make sure the chiral center is inverted. You don't have to, but I would just to double check. Because I'm going to be checking. So then for the SN1, all I did was now I've got so now I've got this, I'm showing the stereochemistry here. So when I'm reacting this with, what did I react it with? Water. So if I react this with water, the first thing we would say is it's a secondary plus a weak nucleophile. What's the critical part? The weak nucleophile, because weak nucleophiles can only undergo SN1. So then this is an SN1 mechanism. Now, how do you know if it's 2 or 3 steps? Is that something you have to memorize? Yes and no. If you do enough of these problems, then you'll learn it. So the critical part is if you think about what am I going to do in this mechanism? What am I going to do in this SN1? Okay, I'm going to break the bond with the carbon and the chloride, and what am I going to make? A carbocation. Then if this was a negatively charged nucleophile, that negatively charged nucleophile would come in, react with the carbocation, and the reaction would be over. Yeah.
So as in one class spin off, like the first thing like simple carbocation and stuff to like the water coming in and bonding. Like, is it possible you just think like an SN2 reaction with like the 2-step or why you have to show it?
You have to show it as 3 steps.
Well, I know the third step's different, but like the first 2 steps, I don't think it's showing in 1 step.
For SN1?
Yeah.
No. So you want the water to like come in and add at the same time the chlorine's leaving? No. Because then you would never form the carbocation. And the SN1, the mechanism of SN1 is critical on forming that carbocation intermediate. If it didn't, then it would be an SN2 mechanism. So for SN1, we always have to show that first step to form the carbocation. And the reality is that's what's happening. If this reaction went by SN2 and the water came in and kicked off the chlorine, then I would end up with inversion of configuration. I would end up with a bimolecular kinetics. The rate would be that less sterically hindered would be faster. And in this reaction, none of that is true. The rate doesn't depend on the nucleophile. The stereochemistry is an inversion, it's racemic mixture, so we have to show the formation of the carbocation because that's actually what's happening. So our first step would be break the carbon-chlorine bond. And we have to form a transition state, right? So what's the transition state going to look like? Transition state. So the transition state here, what's going on in the first transition state when I break the carbon-chlorine bond? Well, first I'm breaking the carbon-chlorine bond. So what's going to be slightly positive? Chlorine slightly negative and a dotted line partial bond between carbon and chlorine. That's the first transition state. Then that's going to form the carbocation. So the carbocation again you're going to have those as close to straight up and down as you can get them with the positive charge on the carbon. Because that's what the carbocation looks like. It's planar, it's trigonal planar, because remember there's these two empty p orbital, or the empty p orbital, both lobes, that are on either side. And that's where your nucleophile is now going to add. So in this case, I would accept just saying, okay, I'm going to take my water and I'm going to add it to the carbocation. If you wanted to, you could show it adding to both sides of the carbocation to form the R and the S. But what the minimum that I'm looking for is that for the final products you write the R and the S configurations of the products, because this is a racemic mixture. So in the transition state then, what am I going to have? I'm going to have my carbon, my CH3, probably straight up and down. I'm going to have my hydrogen. I'm going to have my ethyl group. And then what am I going to have for the water? A delta or a partial bond, a delta positive on the oxygen, and a delta positive on the carbon. And again, if you want, we could write that from both sides. With a delta positive and a delta positive there. So we could show the transition state if we wanted to, reacting on both sides of the carbocation. But the bare minimum you have to have is just one of those two. Hannah?
Why is there a
Because the next product's going to look like this. The oxonium ion that's formed next is going to have a full-blown positive charge. Right, so when the water adds, the carbon is no longer positively charged. I have a +1 species, +1 overall charge here. There has to be a +1 charge over there. And so the oxygen, what's the formal charge on the oxygen? It owns 1, 2 in the lone. It owns 1, 2 in the lone pair. It owns 3, 4, 5. It came with 6, and so therefore that's its formal charge. You don't have to. I'm just reminding you that that's why it's adding. That's why it's adding to both sides. So you don't necessarily have to show that. If you had to show this empty p orbital. And you don't have to, but I'm just showing it to remind you, why is the water going to add from one side and the other? Because ultimately, you're going to have to show both the R and the S products stereochemically. So I showed the water adding from the right, adding from the left. Now I've got the oxonium ion with the water on in the plane bond to the right, the water's in the plane bond to the left, and so now I have my oxonium ion. So we would have drawn that, right? And I'm saying, if you don't want to show the stereochemistry of these two, you can show one, but in the final answer, you've got to show the final product. You got to show both R and S. Well, the final product's going to be loss of H plus. It's going to be to lose the H plus off of the oxonium ion.
No.
Both of them.
Okay.
Both of them are going to be the products. We get two products because we get a racemic mixture. Okay, so all I did was copy and paste because I can do that. Hopefully you still have space to continue on with these two. Okay, so then what's the final step in the mechanism? The final step is to break an OH bond, and lose an H plus. Does it matter which hydrogen I lose the H plus from? No, either one. So in this case, let's take the top OH bond, and the pair of electrons is going to go from the bond to the oxygen. And down here, the bond is break the bond, give the pair of oxygens, give the lone pairs back to the oxygen. And as we do more of this, what I find is this is the bond. This arrow causes people the most amount of problems. If you're going to have problems, this is one of the areas where you kind of have a problem. So remember, the arrows are the movement of electrons. And the electrons always move towards the delta positive or the positive species. So in this case, the arrow goes towards the oxygen. The arrow doesn't go out into space, which happens a lot. It's pointed towards the oxygen. And so when it does that, what's my transition state going to look like? Bless you. So when you're doing the transition states in SN, when you're doing the transition states in your SN1 reactions, the delta always goes with the partial bond. So I'm breaking the HO bond, that's my partial bond. So now I put my charges in. And if you don't like to do the transition state before you've done the final product, then leave some space, do the final product, which in this case would have been, having the OH group with now the lone pair back on the oxygen plus an H plus. So that would have been your final product. So now all we do is we just take the average of the two structures to get my transition state. So what bond got broken? The OH bond. Charge of +1, 0. Charge in the transition state. Delta positive, oxygen going from +1 over here to 0 here. Delta positive on the oxygen. So if you have to, write the product and then average it out to get the resonance hybrid. But remember, the resonance hybrid is also telling us what is going on. So what's going on? I'm breaking the OH bond. What does it need in the transition state? A dotted line. The positive charge is going from the oxygen to the hydrogen. So each one of those gets a delta positive in the transition state. When I'm grading this, and it's an SN1 reaction, and I've given you a stereochemistry to begin with, I'm going to want to see both stereochemistries of the product. I'm going to want to see both enantiomers. So delta positive, there's the transition state, and then there's my final product plus an H plus. Now,
Do you have to show the whole pathway for both, or if you get to the final product for the different
so I'm showing you the complete mechanism of adding the water, showing the adding of the water of the left and the right hand side. If you want to show the water adding to one of those two sides, that's okay. But in the final product, I'm going to want to see both the R and the S products. So if you wanted to leave out the top part of this mechanism or the bottom part, that's fine, but I'm going to want to see both R and S configurations of the products. That would be what I would ideally like to see. If you want to put it down and say both R and S to indicate that you know both R and S are formed, but you don't write them, I'll give you some credit, but I won't give you full credit. Cameron?
You have to show the lone pairs as well.
That would be really helpful. Helpful for both of us, because then I use less red pen to grade and you get more points. So, but where do you want to show the transitions or the lone pairs? Lone pairs are not in the transition state, so you're going to want to show the lone pairs in the reactants and products. So yes, you're going to want to show those. I mean, for the most part, I'm showing you the complete mechanism because that's what I want to see.
So both the R and the S, the OH is in the
Yes. So yes, because the way I had the transition state, if I go back here, the way I had this transition state was that those bonds were up and down. So when the OH comes in, it's going to come in the plane of the paper from the left or the right. So when it's all said and done, it's going to be in the plane of the paper. So I've got two bonds in the plane, one behind, one forward, so that we can do our R and S and so that we can get the tetrahedral geometry. So this is a more complicated SN1 than this is the most complicated SN1 I can give you, because I've given you a stereochemistry of the alkyl halide to start with, and so you have to show the stereochemistry reacting. If there is no stereochemistry shown, then it becomes a little bit easier to write, because then it doesn't matter what groups are on the bold, what groups are on the dashed. So this one is R. Over here on this structure, it goes oxygen's number 1, so it goes oxygen number 1, ethyl number 2, that's number 4, and that's number 3. So over here, this is the R configuration. But down here, what's also formed 50% of the time is 1, 2, 3, and then 4, so this is the S. So because I have to add the water from the left and the right, I'm going to get the R and the S in 50-50 proportions.
So there's one of these transition states the first one is the breaking the chloride.
That's number 1.
The second transition state is the end of bond gas.
Number 2.
And the third is the breaking of the hydrogen.
Right, the OH bond to get it back to being a neutral oxygen. That's number 3. So there's 3 transition states, there's 3 steps, there's 2 intermediates. Jane?
So after the break, the bond with that it's just really oxygen.
Right. So you could either forget about it, or you could say up here minus Cl minus, or down here you could put plus Cl minus. It's important in the fact that it's being produced, but it's not the real action of the mechanism. So I tend to focus on where the action is. So if you were to lose the chlorine, I wouldn't take any points off for that.
So you have to go in the final product.
Yeah, it's not something that it's a high priority. It's there, but it's not something that if you don't show, I'm going to take points off. If you do an SN1 reaction and you don't show any stereochemistry, you're going to get half credit, because you're showing one product when you should show both. If you say both R and S, you might get, 3/4 credit. If you show both of them with the correct structures, then you get full credit. So you're going to have to do an SN2, you're going to have to do an SN1. The SN1, like I said, this is the most complicated one. The other ones, if there's just regular bonds, then you have to write the transition states and the final products. If it's a negatively charged nucleophile, it's just 2 transition states, an intermediate, and the final product. If it's a neutral nucleophile, it's going to be 3. If I said go through and write this mechanism again using CH3OH, yeah, I don't understand why that's going to be like, oh my god, I can't do that. Because here's the secret to it. HOH and CH3OH. So if I could change this mechanism over, all I'd have to do is just say, okay, down here, CH3OH, arrow, adding to the carbon. Over here, what happened to one of these H's? They become a CH3. Over here it becomes a CH3. Over here it becomes a CH3. Over here it becomes a CH3. And then on the second page, on the second part, the only question is, so if I have a CH3 here and a CH3 here, what am I going to lose? An H plus or a CH3 plus? Why? Why do I get a H plus instead of a CH3 plus? So when I do an alcohol, I still lose the H plus. I never lose the alkyl group. H plus it's an H plus. What's a CH3 plus? Because if I break the bond and I form a CH3 plus, what have I done? It's a carbocation. Is it a stable carbocation? Hell no. Right? It's worse than a primary because it's a methyl. So it's absolutely not stable. But it's not stable compared to losing an H plus. So the mechanism is identically the same, except you can't lose the alkyl group if you do this with an ether. So when I switch this over and say, oh well, let's do this with a methyl group, don't just go, I can't do it, because you can. You just do it like water, and then erase an H and put an alkyl group in. It's exactly the same mechanism. CH3OH is just like HOH, except one of the hydrogens is now an alkyl group. Cameron?
So when you said that's for a hydrogen level, then that's two reducing.
It's 3 steps if it's a neutral nucleophile. It's 2 steps if it's a negative nucleophile. So this is where when you're doing these, so when you're writing these mechanisms, think of what you're doing as you're writing this. Think about what the step is. So the first step is to break the carbon halogen bond to form the carbocation. The second step is to have the nucleophile come in and attack that carbocation and form the product. If it's a -1 charged nucleophile, the negative and the positive will cancel each other out and will form the final product. Right? I'm not seeing any yeses or nos, or if you have a carbocation and you have like an OH minus, when the OH minus comes in, that's the carbocation and you're done. Right? Because it's +1, -1, you get back to neutral. If it's a neutral nucleophile that adds, what do you end up with? The oxonium ion. Am I done? No, because I've got to get rid of the H plus in order to form the neutral product. So a neutral nucleophile, and we only got 2, water, alcohol. If you add those, you're going to have a third step because you've got to get rid of the H plus. If it's negatively charged, 2 steps is all it's going to take. So as you do that, kind of think through, what am I doing? When I'm writing my transition state, what bond am I breaking? Dotted line. What bond am I forming? Dotted line. What are my charges? Average of the reactant and the product of that step. Or if there's if something starts out with a positive charge, and it gives it to the other one's going to be a neutral. It's going to transfer that positive charge from carbon to oxygen. Hannah.
Could we do an example of
An SN1 with 2 steps, sure. How about this? Oh, let's see. We haven't done anything with cyclohexane rings yet, have we? Is that gonna throw everybody for a tizzy?
Yeah.
Then I think we need to do that then. Not yet. That's E1. That's E1. Here, I'll put the double whammy on you. Oh wait, you wanted 2 steps. There. So can you, because when I think you said can we, I think you were talking about we, not we at the moment. Can we write this mechanism of this SN1 reaction? So let's do this. We got our 5-minute break here and then do this. And see how far you can get on your own. And then then we'll go over it. Lost. Well, everybody was here, so. So what's an elimination reaction? Substitution, we're substituting one nucleophile for another. Right now, all we've done is halogens. Halogens have been what we have been substituting for. So let's start with halogens and let's talk about what is an elimination reaction. So an E reaction stands for elimination. What am I going to eliminate? Well, if I take an alkyl halide, let's write the mechanism here, and then it'll be clear what we eliminated. So this is a secondary halide, and let's say that I have a secondary halide, but I have no nucleophile. Can I still lose the carbon-chlorine bond? Sure. So if I lose the carbon-chlorine bond, I'm going to have, what am I going to form? I'm going to form a carbocation. Have we done this step before? Yeah, we just did it like a few minutes ago. So this is the first step in SN1. But what if there's no nucleophile that can substitute that can add to the positive charge? Or what if the nucleophile is slow? Or what if I raise the temperature and give the molecule a lot of energy? What can happen? Well, here's what can happen. I can lose an H plus from the carbon that's attached to the carbon with the plus charge, to the carbocation. So I can lose a hydrogen attached to the carbon with the leaving group. And if I lose that hydrogen and that chlorine, I could basically lose HCl and form a double bond then between those two carbons. For the sake of argument, I'll call this carbon 1, carbon 2, carbon 1, carbon 2. So if I lose a hydrogen attached to the carbon, attached to the carbon, attached to the leaving group, then I can form a double bond by eliminating HCl. The mechanism by which this would happen is I would lose the chlorine first to form the carbocation. So I got to be able to form a secondary or tertiary carbocation in this case. And then what would happen is then this pair of electrons in the hydrogen, I would break that carbon-hydrogen bond. I would lose an H+, and then this pair of electrons from the hydrogen is going to go to form the double bond, so that way the carbon with the positive charge gets its 8 electrons back that it's sharing. The H would eventually bond with the chloride, yes. And in this case, since there's no water, because if there was water, the water would add to the carbocation. In this case, since there is no water there, if I did this reaction, I would actually see HCl gas spit out of my reaction. And the final product I would make then would have the double bond form between, in this case, carbons 1 and carbon 2. So this is an elimination reaction. I'm eliminating HCl from my molecule to form an alkene. If I think about the mechanism, whether it's a 1 or a 2 mechanism, let me take a step back here and think a little bit about the steps. So I had the same first step as an SN1. And if I do that, then I'm going to call this an E1 mechanism. So the rate determining step is going to be the formation of the carbocation. So this is going to be E1. The rate's only going to be dependent upon the alkyl halide. Then again, in this molecule, or in this reaction, that's all that was reacting. So this is E1 elimination. Whenever you have E1 eliminate, well, whenever you have SN1 elimination, or SN1 and E1, you're going to have those together. Because if you think about the first step, if I can form a carbocation, my leaving group leaves and I form a carbocation, now it's a question of timing. Does the nucleophile get to the carbocation before I lose the hydrogen? Are they about the same rate? And so in general, what we're going to say is when you get SN1, you're also going to get some E1. Now you can maximize the E1 by having no electrophile. Or sorry, no nucleophile to add. You probably have to elevate the temperature. So if you heat an alkyl halide to an abnormally high temperature, it's going to eliminate HCl. And you're going to get an alkene. So SN1 and E1 are, since they share the same common first step, they're going to go together. So on my table that we drew up yesterday, everywhere there's an SN1, you could put SN1 plus E1. And we're going to come back to this and talk about how we do this reaction when I have an OH leaving group, which, if you're thinking about yesterday, would be like, wait, you said OH can't leave. Well, I said, actually, we have to do something special to the OH to make it leave, which we'll learn about doing. But E1 and SN1 go together. Would be this one plus an H plus plus a Cl minus, and those would probably combine together.
Okay.
I'm more interested in the alkene product. There's a lot of things in this alkene product that I need to talk about. First of all, I need to use this terminology that showed up, I believe, in chapter 6 or 7 in one of the top hat problems. It is very inconvenient of me to say that in an E1 reaction, I'm going to lose the hydrogen attached to the carbon attached to the carbon attached to the leaving group. I can say that all day, but it's kind of unwieldy. So what we instead do is we're going to give these carbons Greek letters. And this is going to stay good until like the last week of class in the next class, when I'm going to redefine alpha and beta. Which is usually why I don't like to use the alpha beta terminology now, but I mean, it's the last week of classes, so we can use this a long way. What's the alpha carbon? The alpha carbon is the carbon attached to the leaving group. What's the beta carbon? The carbon attached to the alpha carbon. In this case, I actually have 2 beta carbons. Because even though it doesn't look like this, I wrote isopropyl chloride. That's an isopropyl group. What would be attached to the beta carbons? The gamma carbons. What would be attached to the gamma carbons? The delta carbons. So we can go down the Greek alphabet here. We're only interested in alpha and beta, because the hydrogens that I'm going to lose are the hydrogens attached to the beta carbons, which are called the beta hydrogens. I'll try. So, from where? Okay. So the hydrogen that we're going to lose after we form the carbocation is a beta hydrogen. What's a beta hydrogen? A beta hydrogen is a hydrogen attached to a beta carbon. And the double bond that I form is going to be between the alpha carbon and a beta carbon. So if I go back and put my alpha and beta terms back in here, I form a double bond between the alpha and the beta carbons. So back in one of the top hat problems, they asked you to, like, how many beta hydrogens are there in this molecule? Again, they love to foreshadow. They're like, well, if we show this to students now, they'll remember it later on when we get to it. They're Canadian, so maybe it works that way in Canada. But ideally, it would be nice if that happened. But a lot of times, there's just a lot of stuff in between there, right? We learned stuff, we lost stuff. So for the beta, so we're going to form an alpha-beta double bond. So if I just wanted to write the product of this reaction, all I need to do is lose the leaving group, lose a beta hydrogen, and form the double bond. So I can write the product or products of this reaction without ever writing the mechanism. Let's try it. So here's 2-chlorobutane. I'm going to do an E1 mechanism on this. How many products do I get? Well, which one is the alpha carbon? There's the alpha carbon attached to Cl. How many beta carbons are attached to that alpha carbon? I got one on the left and one on the right. Do they have hydrogens? Yes, because without beta hydrogens, you can't form a double bond. You can, but it'll have 5 bonds. Okay? So if I was going to do the mechanism, I would say, okay, let's break the carbon-chlorine bond. And I'm going to form my carbocation. Now, for each of the two beta carbons, let's call this beta carbon 1, and let's call this beta carbon 2, I'm going to show the H's. So I've got beta hydrogen 1 and beta hydrogen 2. And what can happen? I could lose beta hydrogen 1, so this pair of electrons can go to form the double bond. And if that happens, if I lose beta hydrogen 1, I'm going to form the double bond to the CH2. So I'm going to call this, I can call this product A or product 1. What if I lose beta hydrogen 2? What am I going to get? I'm now going to form the double bond into the middle of the molecule. So this is E1 because I'm forming a carbocation. And I should take a step back here and say, I'm now going to broaden my definition of 1s and 2 reactions based on whether they go through a carbocation intermediate or not. So all reactions that have a carbocation intermediate, what are they going to be? A 1 or a 2? If that's my definition of 1 and 2, all the reactions that have carbocation intermediates are going to be what kind of reaction? A 1 or a 2? A 1. Right? All the 1, whenever I say that's a 1 mechanism, it has to have a carbocation in the mechanism. If it's a 2 mechanism, it won't. Okay? So I can broaden that definition of 1 and 2 out and just say, okay, 1 and a 2. So this is still an E1 mechanism. Why? I'm eliminating, forming a double bond, and it goes through a carbocation intermediate, E1. Question. Are these two products different structural isomers? How do I know the answer to that? They're different structural isomers if they have different arrangements, but what if I don't deal with arrangements? What if I have a difficult time? Different structural isomers have different names. You know two molecules are structural or constitutional isomers if they have different names. Does that make sense? You know two molecules are structural isomers if they have different names. Different IUPAC names. So if I asked you, are these two products different or the same? Different, you might say, well, one's got a double bond to the end and one's got a double bond in the middle. Now sometimes that's easy to see, sometimes it's hard to see. So I could say, what's the name of the first one? And you would say it's 1-butene, or but-1-ene. And what's the name of the second one? But-2-ene, or 2-butene. Different names, different structures. Okay. So I just did a reaction that has two different products. Is anybody psychic enough to predict what my next question would be? That's a good question. Which one is more stable? No, that's a good question. Which one's more likely to form, and we call that the major product. And in major product, it's always whichever one has the highest percentage. You need not have a majority to win. So in this case with 2, if there were a whole bunch of side products, all you need is the highest percentage. If these are the only 2 formed, it's 50.1 to 49.9. Do I ever get down to dealing with those numbers? No. But do I need to predict what the major product will be? Yes. How do I do that? I need to know the rule. So the rule for this was actually determined by a Russian chemist called Zaitsev, or sometimes the E's or V's. I think in the past I've seen this as Zaitzev. Problem is it's Russian translated into German, translated into English. But Zaitsev actually did a whole bunch of reactions, elimination reactions, and what he found was that every time he did the reaction, he got the more substituted product. And so it became the Zaitsev rule. The Zaitsev rule is that the more substituted product is the major product of the reaction. Now, what do I mean by that? An alkene, a carbon-carbon double bond, can have a maximum of 4 things attached to it. Right? I'm saying that like you've never heard of that before. But all we have to do is go back to last week in E and Z, and that's when we first encountered that. So I've got a maximum of 4 things. So the question is, how many alkyl groups are attached to that double bond? The more substituted it is, up to 4. Now, for product B, which would look like this, how many alkyl groups are attached to the double bond? 2. Now, you could say, well, against all fundamental educational principles being in the last minute, at this point I don't care. When I go to cyclohexanes, everybody gets freaked out. It's like, I don't know, how many alkyl groups are attached to that double bond? 3? And you might say, Well, if initially you have a difficult time counting alkyl groups, let's count hydrogens. Because if there's 4 things attached to this double bond, and how many hydrogens are there? 1. That leaves 3 alkyl groups. Alkyl group 1, alkyl group 2, alkyl group 3. So if you don't like to count alkyl groups, count hydrogens. And then subtract from 4. So what we need to talk about with this E1 reaction is the major product is the one that is most substituted. Why? Well, Zaitsev didn't know why. He just knew this is what he got. So then later on people said, why? And it turned out that the more substituted alkene was the more stable product. And on Monday after the exam, we'll talk a little bit more about, well, what makes that stable. All right. So remember that next week is a short week. Short by 1 day, because 4th of July we don't have classes. They didn't build in an extra day. But so next week will be, so after the exam on Monday we'll have class on Tuesday and Wednesday. But then the final week after that, we have an exam on Monday and then the final exam on Thursday. And then you get 3 days, and then we start up in Organic 2, for those of you who will stick around. That, I think you're going to have your lab final exam.
I mean, like, good.
Oh yeah, no, you don't have, 4th of July is off for everybody. All classes. Okay? So I will send you, again, just a list of what I anticipate to be on the exam. If you have any questions, shoot me an email. Keep your eye on the discussion board, because if I get any questions and I record a video, I will throw that up on the discussion board.
Thank you. I just want to make sure I have the homework.